That's why Mr. Park has left. It's just because he got so fed up with our class. What is it? Why do they keep talking about 69? It's March. What are they talking about under that speech? You can get the mustache. Oh, that's classic. Yeah. Wait, I remember this from whatever. That other guy. What's that BS?
So, frames per second. All right, photons are waves and particles at the same time. This is called duality. It's a property of actually matter as well, as we're going to find out. Matter exists as a wave and a particle at the same time. That's what a de Broglie wavelength does. Now, you can only see them one at a time. You can only witness them as a wave, or you can witness them as a particle, depending on your experimentation. You can't actually do an experiment which proves both of them at the same time. We'll go through two primary experiments, which show them as a particle and a wave. Yeah, kind of like that. You just don't know until you look at it. Your physical act of observance makes it one way or the other. For the particle, it kind of goes along with that, but not entirely. That has to do more with the position versus momentum of it. For the particle, we're going to look at the photoelectric effect, which is primarily what Einstein won his Nobel Prize for, not relativity, as a lot of people think. So the photoelectric effect shows light as a particle, as a chunk of energy.
It travels like a wave.
Yes. And diffraction shows it as the wave nature. Wave nature. To see light as a wave, we look at diffraction patterns. So shining a light through a CD, for instance, or shining it through a diffraction grating, how it splits the light up into, makes it act more like a wave. So those are the two primary ways you can look at either the particle version of the light or the wave version of the light. And actually, it's both at the same time. What we're going to start with is the particle version. The particle of light is called a photon. Now, I shouldn't, I guess, say particle. A photon, sorry? It is more like a packet. Yeah, it's not really a particle of light. Particle indicates that it's got some mass and some volume. In reality, a photon is just a packet of energy. It's just a moving energy, basically. It has no mass, has no volume. It has a set speed. You know what the speed is? The speed of light. Any photon is going to move at that speed. And because we're talking about wave particles moving, or wave motion, we can use the equation v equals f lambda like we did for all the other waves. Where instead of velocity, we're going to use c for the speed of light. F is frequency. And lambda is wavelength. Wavelength.
It's all about the rap letters.
We can use c equals f lambda to calculate frequency and calculate wavelength. And photons will, because they're waves, have those features. And then we can use those features to determine other things in the quantum world, like how much energy a single photon would have. It's not the best way to do it, but I always imagine a photon like a ball. It has momentum too, even though it doesn't have mass. We'll talk about that later. But ball moving at the speed of light. Basically, it's a photon. It's a packet of energy. Now, the energy of that light, the energy of a photon, depends on its frequency. The energy of a single photon equals hf. E in this case, energy of a photon. This energy can be given in 2 units, joules or electron volts. We'll talk about electron volts later. H is Planck's constant. It's got a C in it. Which we'll identify in a minute. And F is frequency. Hertz. Planck's constant is in joules times seconds, or it's in electron volts times seconds as a unit. Now, electron volts are actually going to be real useful when we talk about the motion of electron in the photoelectric effect. Because instead of coming up with some weird number of joules that it takes to stop an electron, we can just come up with a nice pretty number of volts which stops an electron. And then multiply it by the charge to find electron volts. We're a little bit ahead of ourselves right there. Planck's constant is a number. Planck's constant, if I remember correctly, is 6.625 times 10 to the negative 34 joule seconds, or 4.14 times 10 to the, I want to say 13.
Is that your final answer?
15. I mean, 15. Electron volt. Because a joule is not equal to an electron volt. They're 2 different units of energy.
But they could be used the same thing.
You can calculate the energy of a photon in electron volts or in joules.
Okay,
And there's
so they're not like interchangeable. Like, it's like finding the difference between
No, it's a conversion.
Okay, so look, if you have 6.265 and 34,
Yes.
yeah, that many, it's the same as having the other, that many of the other.
These 2 numbers are the same with different units. If you're going to calculate energy in electron volts, you have to use the bottom number. Yeah, it's exactly like that. Sometimes you want to use a centimeter, sometimes it's more convenient to use a meter. It's just conversion between the 2. The conversion, in case you need it, which you may, 1 electron volt is 1.6 times 10 to the negative 19 joules. And that number should look familiar because it's the charge of an electron. That's why electron volt is actually a very useful unit when you're talking about electrons. They're not, but electron volts and joules are.
No. So an electron volt has nothing to do with voltage.
It does.
It's not a voltage. Don't rip yourself. Let it rip you. Don't make it any worse.
Did we do this? Did we do this equation?
No.
Potential energy due to a voltage.
No.
When you have an electric field, this is getting a little bit ahead of ourselves. When you have an electric field, we drew the equipotential surfaces. There were equipotential surfaces. We did it. We put the electric field in water and then found the voltages at different places and then mapped them out. So let's say that this was a 1 volt potential and this was, 2 volt potential, or negative, I guess. Well, if I take an electron, say I take this electron right here, and I move that electron to this position here, I've moved it, and in moving it, I've used energy. Right, to move it. Well, let's say it's a proton. Gaining or losing energy, it doesn't matter. The energy is changed from one place to the other. Do you agree with that?
Yes.
Okay. The energy changed from this place to the other place. If I moved an electron, yes. Because the energy that I used is the charge that I moved times however much voltage I moved it across. So if I take an electron and move it from here to here, yes, I've used 1 electron volt of energy. Or I can multiply the charge times voltage and get how many joules of energy I used. So it's just more convenient if I'm moving electrons to use electron volts as a unit of energy. That's